Shut up and sit down.
Well, hey everybody, welcome back to our 2020 National Electrical Code series here on Patreon. And today's episode, we're moving into part 5. We are still in definitions because definitions are critical. I always like to believe that when you build a building, you have to make sure the foundation is solid. So I think of definition as the foundation. Now we're going to move through the code. There'll be graphics that we show as we get into the different aspects of the code. But I believe that there's fundamentals that we have to follow, okay? And this is one of them, and that is understanding the definitions, okay? So bear with me, watch them, get a better understanding of them, and they're really going to serve you later as we move through the code and you see these terms and you're like, God, I saw this somewhere. Or now I have a better understanding of what it is. So stay with me. All right, so now we're moving in, again, part 5. So we're going to go to ungrounded conductor. Or ungrounded, I should say. So what does ungrounded mean in the code? Because we see it a lot. We have ungrounded conductors, we have ungrounded systems, and basically it means there is no connection to ground, or it's not connected to ground, or to a conductive body that extends that ground connection, or the ground connection. So under the purview of Code Making Panel 5, I do serve on Code Making Panel 5. So this one, basically, an ungrounded conductor is your hot conductors that is not connected anywhere to ground. Otherwise, it'd be a short circuit, ground fault, right? All right, so, but you have what's called grounded conductors, which a conductor is intentionally connected to ground, okay? But an ungrounded conductor, for example, is not. But here's a term, ungrounded, which is broadly used to say I have a system from a transformer that is an ungrounded transformer, okay? That means I don't have any connection to ground. All those conductors that are coming off of it are considered ungrounded conductors, and it's an ungrounded system. Okay? So that is what it is. Something that's considered ungrounded does not have a connection to ground or any conductive body that actually extends that connection to ground. Okay? It's considered ungrounded. UPS system. We hear people talk about UPS systems all the time. It is a power source. It is a power supply used to provide alternating current power to a load for some specific period of time in the event of a power failure. So many people use an UPS as a power source. Okay, and again, it's just you buy it as a system, and it can be utilized into the system as a uninterruptible power source. Okay, it means it just goes. It doesn't cut off on it. It just provides that alternating current for a specific period of time. In an event of a power failure, then they come on, and you have a UPS system that does that. Okay, it does have an informational note that says, in addition, it may provide a more constant voltage or frequency supplied to the load, reducing the effects of voltage and frequency variations. So a lot of times you'll have systems, for example, that have transfer equipment, normal generator, and they will also have a UPS systems in it to kind of smooth out that transfer of power. That's one application. So again, there might be systems that have a variance in the voltage or frequency, and a UPS system can be used, okay, to help smooth it out, if you will. Smooth it out a little bit because a UPS system provides a constant voltage. You won't have any dip in voltage, okay? The frequency is very constant, okay? So a lot of times they're used as well as what we say conditioning to a system, right? All you really need to remember, it's a power source that provides alternating current for a specific period of time based on the capacity of the UPS, and it's used in cases of power failure. All right? But again, it can also be used to reduce the effects of voltage or frequency variations in a system. All done by the design professional. Okay? All right. Utilization equipment. Very broad, used a lot. What is it? It's equipment that utilizes electric energy for electronics, electromechanical, chemical, heating, lighting, or similar purposes. So when people say I have an outlet box and I connect the luminaire to it, basically that luminaire, if you will, is a luminaire, don't get me wrong, but it is also connecting as utilization equipment. So if I'm connecting to an outlet and it says, remember the definition of an outlet is a point where utilization equipment can make a connection to it, then again, if it is involved with electronic, which is electromechanical, chemical, lighting, heating, or similar, then if it's a piece of equipment that utilizes that function and it connects to the system, then that is called utilization equipment, okay? And an example of utilization equipment might be a unit heater that is connected to an outlet. And again, since that equipment is connected, that's utilization equipment. It's generating heat, okay? But it's connected to an outlet, okay? And that's the point where you take electrical energy from the system, okay? But the piece of equipment qualifies as utilization equipment. And it's a bigger all-encompassing definition than to try to define every piece of equipment, okay? All right. Voltage. We should know what voltage is by now. The voltage of a circuit. It is the greatest root means, RMS, I'm sure you've seen it, the greatest root mean square effective difference of potential between any two conductors of a circuit concerned. Basically, Informational Note says some systems, such as three-phase 4-wire, single-phase 3-wire, and 3-wire direct currents, may have various circuits of various voltages, okay? But basically, the voltage is the differences in potential of voltage difference between two conductors of the circuit, okay? That's how you create a voltage. It's a difference of potential. Now, what's nominal voltage? Well, the nominal voltage is a nominal voltage assigned to a circuit or system for the purpose of conveniently designating a voltage class. So when we say nominal, something might be voltage, might be, let me give you a good example. This might be 460 for motor. That's the voltage of the circuit, maybe, or I guess we should say. Maybe that's between two conductors is the voltage is whatever it reads out to, it would be whatever the voltage is, okay? The nominal would be treating it at a 120 when you might get a reading of 121. That is the true root mean square value, RMS. That's why we have meters, RMS meters. But the nominal value, okay, is what we use for example, to get 120, to be able to use 120, okay? Now, some informational notes here. We'll read them to make it relevant. It says, informational note, the actual voltage at which a circuit operates can vary from the nominal range within a range that permits satisfactory operation of the equipment. So you have a nominal, but it could be a little above 120, could be a little below 120, okay? But it's 120 nominal. We're permitted to use the nominal. For example, we do motors. It might be a 460 volt motor, but if you go back and look at three-phase and you go look at 430.250 for the FLC, you'll notice that up in the charging statement, it will say that it's 460, but you can take it as 480. Okay, that's the nominal, all right? And then, of course, you've got other informational notes. And then you got here certain battery units may be considered to be rated at nominal 48 volt DC. Lead acid maybe or something is nominal 48 DC, but may have a charging of floating voltage up to 58 volts in DC and 60 volts used. 60 volts is used to cover the entire range of floating voltages. Okay, so that might be the voltages, but the nominal might be stated as 48 volts. You with me? All right. Again, just know that voltage is a unit of voltage pressure as well, and it is, again, the difference between 2 points is voltage. That's on the circuit, but we use nominal voltage, okay, for most of anything that we do in calculation purposes, okay? Voltage to ground. So for grounded circuits, the voltage between the given conductor and that point on the conductor of the circuit that is grounded. For ungrounded circuits, the greatest voltage between the given conductor and any other conductor on the circuit. Okay, so voltage to ground would be, let's say, any of the ungrounded conductors. Okay, grounded circuit conductor. That point to the conductor on the circuit that is grounded. So I'm taking a voltage measurement. That would be a voltage to ground. So if I go from one of the phases to ground, that would be the voltage to ground. Okay. And again, that's on grounded circuits, okay? Circuits that are actually connected to ground. That's for grounded. We have for ungrounded circuits, but let's just talk for grounded circuits. So it's actually the voltage between a given conductor and that conductor that's connected to ground. So from hot to the neutral, because that's connected to ground for a grounded system. That's going to be the voltage to ground, which would be 120, for example, on a 240. The phase to phase, then you have voltage to ground. That's how you get the 120, voltage to ground. On an ungrounded system, it's the greatest voltage between any given conductor, whatever the conductor would be, and any other conductor in the circuit, okay? That would be voltage to ground. It's not necessarily to ground, though, but kind of let that go for right now. Now, the reason I say that, because you could have an ungrounded system, and you end up taking an ungrounded system, and then you corner ground it, and it becomes a corner grounded system. And again, that's from that conductor, any conductor to that conductor, again, would be voltage to ground. Watertight. Constructed so that moisture will not enter the enclosure under specific test conditions. So remember we saw rain tight, and we wondered what it was. Now we see something that's rated watertight. Now, watertight is constructed so moisture will not enter the enclosure under certain conditions of its test. So if it's something that's watertight, then it is designed so that water will not enter it at all. That is watertight. Now, waterproof. It's constructed or protected so that exposure to the weather will not interfere with successful operation. It's not watertight, okay? But it is waterproof. So it's designed in a way that is either constructed or shielded in some way that if it is exposed to weather, like a NEMA 3R is weatherproof, then it is done, or a weatherproof box. It is designed and protected so that exposure to the weather will not interfere with the operation. Okay, so in other words, it's designed so it can't get to the critical terminal points and things like that that could affect the operation of it. Okay, so if that's the case, that was meant to be waterproof. Now, waterproof, again, is condition where moisture will not enter the enclosure under specific conditions, period. Weatherproof is different. Weatherproof is just proofing it for weather. So it's exposed to the weather outdoors, and it will not interfere with its operation. Doesn't mean it's not going to have weep holes and water can get in there. Now, it could be weatherproof and watertight, but chances are it's either going to be weatherproof or watertight or even rain tight, depending. So make sure you look at all these definitions routinely. Things get confused here. Now, there is an informational note, and it says, rainproof, rain tight, or watertight equipment can fulfill the requirements of weatherproof. Obviously, if it's watertight, moisture can't get into it. So as you can see, we have an overlap here. Rainproof, rain tight, and watertight equipment can meet weatherproof, but weatherproof won't necessarily meet those other conditions. Okay. And it says for weatherproof, where varying weather conditions other than wetness, such as snow, ice, or dust, or temperature extremes, are not a factor. Okay, so I can use rainproof, rain tight, watertight enclosures. They can meet the requirements of weatherproof. Again, where varying weather conditions other than wetness, such as snow, ice, dust, or temperature extremes, are not a factor. Okay, so I get some overlap to work with that. Okay, now part 2 deals with over 1,000 volts. Okay, and we're not going to cover a whole lot of this. I want to cover some pieces in here. Obviously, we're dealing with fuse when it comes to over 1,000 volts. And a fuse is an overcurrent protected device with a circuit opening fusible part that is heated and severed by the passage of overcurrent through it. So it has a specific, it can handle a certain amount of overcurrent, and then the fuse just melts away. Okay? Again, that's for over 1,000 volt nominal is where we're at now. Okay? You have a bunch of different types of fuses. We're not going to go over each one of these, but I just want you to know they're here. Okay, you have circuit breaker definitions as well. That is very specific to over 1,000 volt. Okay, it is a switching device capable of making, carrying, interrupting currents under normal conditions, circuit conditions, and also making and carrying for specific time and interruptive currents under specific abnormal circuit conditions, such as those of short circuit. Same definition. Some of these are exactly the same definitions, folks. It's just specific to over 1,000. So, for example, we have circuit breaker here. And if we go back, I just want to point out that we go back here, we have circuit breaker here as well. And you notice it's same, pretty much close to the same definition. Close. The only difference in the part 2 here, if you bear with me here as I get to it, is that, hold on, right here, circuit breaker, right here, you notice it doesn't have anything in said about a non-automatic or that type of stuff. It doesn't have this. It doesn't have exactly the same language. Okay, all right. So that is that part. So we're going to now move into part 3, and again, part 3 we're just going to kind of go over the definitions, and when we get to hazardous locations, we'll speak into them in more detail. But now we're in part 3. And part 3 came to us new here in the 2020. Okay, so part 3 is a combination. It was added in the 2020 code to bring all of those definitions that had to do with hazardous locations and relocate them in a definition 100. Okay, because they were up in 500 and it's spattered through 501, 502, 503. 501 is gases and flammable vapors in liquids. Class 2 is combustible dust and things like that. And then class 3 was flyings and fibers and things like that. So you had these definitions, and some of the stuff overlapped. So what we've done is basically just move those definitions back to Article 100 and created a whole new part. Okay? So, for example, we know what an aircraft paint hanger is. Obviously, it's for painting aircraft. But we're making a reference in 500 or 501. It might make a reference to aircraft paint hanger. And we have a definition of what that actually constitutes. Okay? Combustible dust. So, when you're dealing in combustible dust and we're dealing with a Class 2 Division 1, or Division 2, we need to know what combustible dust is, or what can constitute it. So it is actually dust particles that are 500 microns or smaller, okay? And they actually are present. They present a fire and explosion hazard when dispersed and ignited in air. So obviously in a 502 scenario, we have a problem in a Class 1 Division 1, and potentially also in a Class 1 Division 2 that we have to be aware of. So anytime it makes a reference to combustible dust, we need to know what the threshold is for that. Now, usually a design professional is going to make that call and say whether it's combustible dust, whether it's a Class 2 Division 1 or Division 2. They'll make that call, okay? But if it's in the air and it's combustible dust, at least we need to know what a definition of, okay? Now, if the microns are greater than 500 microns, then it's not considered combustible dust. And so real important to understand what the definition is of a combustible dust. Okay. Of course, there's also some standards here that you can read if you're really want to get into the details. You got a couple ASTM standards here that you can look at. These standards tend to be pretty expensive, so as an electrician, I tell people don't worry about it. The designer has to worry about this, not you. All right, so they're the ones that have to do that. Okay, here's another one, dust ignition proof. Now, this has to deal with equipment. So since we're migrating from a combustible dust condition, and obviously when we get up into 501, 502, we're going to discuss things like seal-offs and all that good stuff. But it is equipment enclosed in a manner that excludes dust and does not permit arcing, sparks, or heat otherwise generating and liberated inside of an enclosure to cause ignition of exterior accumulations or atmospheric suspensions of a specified dust on or in the vicinity of the enclosure. Okay, so again, I have dust ignition proof in its equipment, and if it gets an enclosure, for example, under the ANSI UL 1202 or 1203, it talks about explosion proof and dust ignition proof electrical equipment for use in hazardous locations. Okay, so it's equipment that's enclosed in a manner that is going to become dust ignition proof. Okay, so it excludes the dust. Okay, and it does not permit arcs or sparks or anything that could happen due to a heat that gets over an ignition level from generating anything inside of the enclosure that could cause ignition. Okay, so all of that, or of exterior accumulations of atmospheric suspension, means enough dust that accumulates that could cause a hazardous condition. So I'm looking for dust ignition proof equipment or enclosures that I might put something in, the equipment in, that is going to limit the accumulation of dust that is easily ignitable or that meets that 500 microns or smaller threshold for combustible dust. Okay, so you do have some informational notes that talk about dust ignition proof enclosures, but you have what's called dust explosion proof enclosures, are sometimes additionally marked type 9 from NEMA 250. That's your enclosure standard for them. And it is NEMA, it's called enclosures for electrical equipment. And again, you probably can find an old edition online for free, but if you have to buy it, it's probably $100, $200 for that. I'm not so sure I would do that because a lot of this information is regurgitated in the NEC later in 110, but just so you know about it. Okay. Now, if something's required to be dust tight, okay, it says enclosures that are constructed so that the dust will not enter under a specific condition. Okay. Now, this is this is different in a sense that when something is dust tight, that no dust can enter, period, under the specific test condition. Again, equipment's only good for how it's tested. So you'll have test parameters. So if something in the code makes a reference to dust tight, then it is actually enclosure. If it says a dust tight enclosure, then it is dust tight. It will literally not allow dust to enter into it. Okay? It's a difference. You have a bunch of different other definitions that we won't go into. You'll run into them and you just need to know they're here. But again, a bunch of different ones that were added to the 2020. If you're disappointed, don't be, because when we get up into 500, 501, 502, 503, 511, 513, we're going to make reference to some of these things. For example, like what the encapsulation M means, and then what we're going to do is go back to the definitions. Okay, so we don't want to spend too much time here. We spend a lot doing definitions, but you can read them. But since I know that I'm going to cover these in nauseous detail when we get to 500, 501, 502, 503, when it comes to certain applications that call for this, that's when I want to talk about it. Okay, so I just don't want to get it too deep right now in those type of things. We're talking about stuff that's necessary. Now, other things that you're going to hear about that you need to know at this stage is things called intrinsically safe systems, intrinsically safe circuit, and intrinsically safe apparatus. Now, you'll run into this when you're dealing with fuel pump dispensing applications, and you'll see them mention intrinsically safe. Okay? Now, in order to understand what intrinsically safe apparatus is, or intrinsically safe circuit is, or intrinsically safe system is, we need to understand what it is from the circuit level to the system level, and then, of course, any apparatus that's associated with an intrinsically safe system. So let's look at each one. What is an intrinsically safe circuit? Okay. Now, probably before we even get into that, we probably should look at a definition of what intrinsic safety is. And it's represented by I. Okay, and that is a type of protection where a spark or thermal effects is incapable of causing the ignition of a mixture of flammable or combustible material in an air under prescribed test conditions. So, intrinsically safe to me means that there's not enough of energy that's created by that circuit or that apparatus or that system that can generate an arc or enough heat that can cause a volatile condition of the surroundings. So it's considered intrinsically safe. And so it's not going to start a chain reaction, okay? So with that said, we then move into, let's look at each one of these. Now, first we look at intrinsically safe circuit. It is a circuit in which any spark or thermal effects, heat, okay, is incapable of causing ignition of a mixture of flammable or combustible material in air under prescribed test conditions, okay? So it's incapable of doing it. So where the code states intrinsically safe circuits are permitted or where you can do that, this is a circuit that cannot generate a spark or have thermal effects that it would be at such a level, means usually it's going to be very limited in its supply, that it can't cause ignition or combustible effect, okay? Now, or combustion to effect. Now, that's an intrinsically safe circuit. Now, we have apparatus that this intrinsically safe circuit will connect to. And this is the apparatus in which all of the circuits are intrinsically safe. So all of these circuits that connect to apparatus that might be in a piece of equipment in a specific area that the code requires it to be intrinsically safe, that apparatus is what's receiving the intrinsically safe circuits, if you will, right? Okay. Now, and we'll talk about this more again in 500, 501, 502, 503, and all this when we see the reference to intrinsically safe. I'll remind you of what we're talking about. Now, what about a system? It's everything. It's the circuit, it's the apparatus, it's the interconnection of the two. All of that is intrinsically safe system. It says an assembly of interconnected intrinsically safe apparatus, which we got a definition for, the associated apparatus, the part that holds the equipment and all that, and interconnecting cables in that those parts of the system that may be used in hazardous locations are intrinsically safe circuits. So in a hazardous location where it permits intrinsically safe circuits, where it might allow you to do something that it wouldn't allow normal circuits to go, but it allows intrinsically safe systems to be in there, it's made of intrinsically safe circuits, apparatus, and all components that are permitted by the hazardous location to be there. You see what I'm saying? Now, an informational note says an intrinsically safe system may include more than one intrinsically safe circuit. Absolutely. I could have an entire system that has apparatus that has a bunch of terminations on it, and all of my intrinsically safe circuits connect to this apparatus that is altogether one complete intrinsically safe system. So when you get to hazardous locations, just kind of remember, if it says it permits intrinsically safe systems to be installed in a certain hazardous location, understand what you're dealing with. You're dealing with systems that cannot generate enough energy or thermal energy effects to cause a fire or to start combustion, okay? A fire from combustion, okay? Due to combustion materials in there, okay? All right, so that's kind of those. And again, we'll get in more detail when we get there for that. Now, another important thing is major repair garage. When we're looking at the definition of garages, repair garages, we needed to know what a major repair garage was, and that used to be in the regular definitions, and now it's kind of here because, again, we have certain aspects in major repair garages, whether it's major or minor, and it has to do with the work that's being done, but we now have a definition. Now, what hopefully doesn't happen is that people don't go to part over into part 1 for the general definition and realize that major repair garages and minor repair garages is not there, okay? But because there's so many things that have to do with the conditions, the floor space, and what goes on in there that could be a hazardous location or not, it seems that it's better served in part 3 here. So you have a major repair garage and you have what's called a minor repair garage. Important to understand the difference in two. What's a major repair garage? It's a building or a portion inside of a building, okay, where major repairs such as engine overhauls, paints, body, fender work, and repairs that require draining of the motor vehicle's fuel tank are performed on motor vehicles, including associated floor space used for offices, parking, and showrooms. Okay, so because you have a major repair garage and you're removing fuel and you have what's called contiguous or whatever they call it, spaces, one space interconnects with another space, so it means that if the floor area is used in office, parking, and showroom is part of it, then that's all part of a major repair garage. Okay, but this is where you're going to do removal of fuel, or that's overhauls. Okay, now what's a minor repair garage? It is a building or portions of a building used for lubrication, inspection, like a Jiffy Lube, and I shouldn't just say Speedy Lube, Jiffy Lube, things like that. It says inspection and minor automobile repairs, such as engine tune-ups, means you're not changing the motor, you're not taking it. Replacement of parts, you're doing fluid exchanges like oil, antifreeze, transmission fluid, brake fluid, air coolant, and things like that. Brake system repairs, tire rotation, and similar routine maintenance included associated floor space used for offices, parking, and showrooms. So that's going to be the repair garage. Now remember, inside of each one of these, you're going to have specific receptacle requirements, let's say for GFCI protection, and it's going to exclude like the exhibition areas or the showrooms, but it's still part of the minor repair garage or the major repair garage. So just kind of giving you. So if I go down to a Jiffy Lube, that is all considered a minor repair. The actual showroom, the area waiting area or the office areas are still part of minor repair garage altogether, okay? But just kind of gives you a good definition of the two, okay? All right. Fuel dispensing facility, where they're going to have the fuel pumps, fuel stations, again, covered in a lot of things like 510 and 511. We'll deal involved in a lot of that type of stuff, and you'll see that's down in the informational note. We could click on 511 just to show you, and it'll bring up, again, commercial garages repair, all right? So you can see what it talks about, and it goes down into it. And here you see minor and major, and that's where it starts to breaking it up, minor or major, things like that. Okay, and then you have 510, which I'm not sure whether you can see. Yeah, I guess you can. And that is dealing with 510, which is hazardous location classified specific. And this is where it's covering things like 511 through 517 and some of the occupancies as part of that. Okay, and it goes into a bunch of different other details as well. Okay, oops, sorry, right here. All right. Basically, 510 is a road map to other things. So, fuel dispensing, again, is where you're going to dispense motor fuel, dispensing mixture from fuel tanks of motor vehicles, marine craft, onto approved containers, things like that, okay? All right. Let's look at the definition of non-incentive versus non-incentive components. Because it kind of, as it applies to intrinsically safe, we need to look at what non-incentive circuit is. What is it? Because you're going to see references to this when you're dealing in hazardous locations. It is a circuit other than field wiring in which any arc or thermal effect produces under intended operating conditions of the equipment is not, okay, so there's an arc or some kind of thermal effect that has, is not capable under the specific test condition of igniting the flammable gas, air, vapors, air, or dust air mixture, okay? So when I see something maybe using a class 1 and 2, division 2, and Class 3, Division 1 and 2, if I'm looking at something that's talking about non-incentive electrical equipment, we see that it might be equipment that can generate an arc or has some kind of thermal effect that's produced as part of its operation, but it's just not enough. It's not capable under the test conditions, and hopefully you're using it within its test condition of generating lighting any flammable gas, vapor, or dust in the air. Okay, so that is called a non-incentive circuit. So just remember, anywhere that the code recommends or states about non-incentive circuits, that you know what it's talking about. Okay, it's a circuit other than the field wiring that is designed usually within the system or within the component that is designed to generate an arc, and it will have heat, but it's not enough that's going to cause any problem. Okay. Now, non-incentive components. Those are a component having contacts for making or breaking and not an incentive circuit. Okay, so we're not talking about a non-incentive. We're talking about an incentive circuit that can produce an arc or thermal effect that could have a problem. So it could be a component that is non-incentive. So it's a component having contacts for make or break, creating an arc, breaking an incentive circuit, and the contact mechanism is constructed so that the component is incapable of igniting specific flammable gas in the air or flammable air or vapors in an air mixture. The housing of a non-incentive component is not intended to exclude the flammable atmospheric or contain an explosion. Okay, so it's not intended to exclude the flammable atmosphere. It's just within itself contain, okay, the incentive circuit that could create the arc. Okay, so it's about the component, right? And you get, of course, you'll get some ANSI standards down here that you can look to if you're into that, okay? And also you have non-incentive equipment, and it is equipment having electrical or electronic circuitry, we're talking about the equipment now, that is incapable, under normal use conditions, of causing ignition of a specific flammable gas in the air, vapor in the air, or dust in the air mixtures due to arcing or thermal means. So it has equipment. Yes, it might have some type of component in it, but in its design, it is not capable of igniting the air mixture, whether it's dealing with gas or vapor or even a dust in the air. It couldn't cause the ignition of that. Okay. And then, of course, we'll end this on the non-incentive field wiring. We'll end this one on non-incentive field wiring. It is a wiring that enters or leaves an equipment enclosure and under normal operating conditions of the equipment is not capable. This is the wiring now. That is not capable due to arcing or thermal effects of igniting flammable gas in the air, vapor in the air, or dust in the air. Or it is under normal operating conditions, includes opening, shorting, or grounding the field wiring, okay? So when the wire leaves it, the field wiring, it's connecting to equipment that might be, let's say, non-incentive equipment or whatnot, but the field wiring that's coming out of it, that is wiring all of these components out in the field, that it doesn't, under normal conditions, the wiring that's going and leaving, okay, this field wiring is not capable due to arcing or thermal effects, producing an ignition in the environment to any gas, vapor, or dust mixture in the air, okay? Now, keeping in mind, you could have a component or equipment that could create something, but it can't do it in a way that it creates something that can affect the environment. Okay, it's got to be contained within it. And then, of course, the other ones you can read, and the other ones that probably not as important for us to cover here. There's two that I will cover. Okay, we have what's called pressurized. So what is pressurized? And you're going to read about this, and we're going to talk about it more in detail. Pressurized, when it defines it in the code, is the process of supplying an enclosure with a protective gas with or without continuous flow. So it could be gas in it, then it's sealed. So it creates a positive barrier so that it's not a negative barrier, which things could get sucked in. It's positive. It's keeping the air out. It's positively, think of pressure pushing against the walls. And it's a sufficient pressure to prevent the entrance of combustible dust or ignitable fibers or flyings. Okay? So it has a certain level of pressure. And as this one applies to combustible dust or ignition of fires. So this one has to do with a class 2 and class 3 when you're dealing with pressurized. Okay. Now we have some other allowances here in a second, but we're just looking at these two. Okay. Now this is keeping out the pressure, so it can't come into it. All right. Now it also says that again it can see with or without constant flow. I could have something that has a constant pressure that keeps getting added to it, okay? And that's what maintains that pressure, difference of potential, pressure differentials, okay? Nothing can get in if something's keeping it from being able to be pulled into the system, okay? I guess the easiest way to explain it. Now, as opposed, for example, to something like purged and pressurized. Now, purged and pressurized is, again, building on something that's called pressurized. And it says it's a process, okay? It's a process of, one, purging, supplying an enclosure with a protective gas, maybe like an argon gas or something like that, a protective gas at a sufficient flow and positive pressure to reduce the concentration of any flammable gas or vapor initially present to an acceptable level. So it's purging it out, getting it out, reducing it down to an acceptable level below those volatile points of ignition, purging it out, getting it out, so that's one step, purging it out. And then it says it adds pressurization. And pressurization is now supplying an enclosure with a protective gas with or without continuous flow at a sufficient pressure to prevent the entrance of flammable gas or vapor, a combustible dust, or ignition fibers. So, in a flammable gas situation, you have a purge and pressure condition, and in purely pressurized condition, it looks like that applies to combustible dust and ignitable fibers and flyings. So kind of two different processes, okay? You just need to understand how this works. Now there's also an ANSI standard. If you're that kind of person that wants to look at it, it's an ANSI NFPA standard, 496, for purging and pressurizing enclosures for electrical equipment, okay? All right, next you just have a bunch of definitions. We have a spray area. Obviously, if you're dealing with a spray application, you've got spray booth, spray room, unclassified area, and that's important. So somebody asked me, so I have a Class 1 Division 1, Class 1 Division 2, Class 2 Division 1, Class 2 Division 2, Class 3 Division 1, Class 3 Division 2. I even have zone systems, okay? And so we're saying those are all classified locations. Well, what is the location that doesn't fall under any of this? That's unclassified. And then why is it important? Because inside of 500, 501, 502, 503, it makes reference to classified locations, but it also says, for example, if you purge and pressurize something, or you lower the level of a certain amount of volatile combustible material in that space, then you can take it out of a Class 1 Division 2, for example. You could remove it down to a lower condition. Or I could take a Class 1 Division 1 and by purging and pressurization, maybe lower it down to another condition. Or in our case here, I could have a Class 2 Division 2 that if I purge it down, could reduce it down to maybe, or a purge and pressurization program, I could get it down to an unclassified location. Also, it's important to things like pits and garages, okay? Maybe the pit is a certain classification, but maybe if I use a certain amount of air exchanges and I put something in place that I could literally remove that from a classified location down to an unclassified location. Why is that important? Because it might it removes all the different things that I might be required with seal-offs and things like that in that area. And that saves money, okay? Now, in order to pressurize it and purge it and do all that, then it costs money for that process. So, again, but you get the point. And then, of course, there's ventilation. And ventilation is providing circulation of a certain air exchange, and it removes excess heat or fumes or vapors. So a lot of times for like pits, you'll see for commercial garages and pits, and they're going to have the ability to ventilate the space. And if you ventilate the space with a certain number of air exchanges, then you can literally change the classification of that space based on ventilation as well. So all those things to kind of remember and get flowing in, okay? So just a really good definition. Now, last one that we'll end on is really, really important, is understanding the volatile flammable liquid. When does liquid become volatile? All right? So here's a good example. So a flammable liquid having a flash point below 100 degrees Fahrenheit, or a flammable liquid whose temperature is above its flash point, or a class 3 combustion liquid, or I say combustible liquid, that has a vapor pressure not exceeding 40 psi at 38 degrees C or 100 degrees Fahrenheit, and whose temperature is above its flash point. Those are all considered volatile flammable liquids. So again, recoup this. Flammable liquids where their flash point is below 100 degrees F. That means it can actually flash over at less than 100 degrees Fahrenheit. And that can happen really quickly. Okay, so keep that in mind. All right, that's one. Also, flammable liquids, okay, that have flammable liquids that whose temperature value is above its actual flash point. So I could have liquids, and I don't know if it's flammable or not, and I look at it, and I see that its actual flammable liquid, it has a temperature that is actually above its physical flash point. Obviously, that's a flammable volatile liquid. That's a no-brainer, okay? That's why it's, puts the or there, okay? So if the flash point is below 100 degrees Fahrenheit, flammable gas, a flammable liquid, okay? It's a liquid. We're talking liquid. Sorry. Whew. Now, flammable liquids, where the temperature actually of that liquid rating is above its flash point, obviously, volatile flammable liquid. Class 2 combustible liquids that has a vapor pressure that does not exceed 40 psi at 100 degrees Fahrenheit, okay, and those temperature, and whose temperature, because it's a two-part here, this is an and whose temperature is above its flash point, then that's considered a volatile flammable liquid. So my advice is when you're dealing with any types of liquids and you're worried about it, obviously it's going to have some marking on it. You get to stop and you get to go and look at the definition, look at the markings, the MSDS sheet, and look at what its flash point is. Look at what its PSIA is if it's, you're dealing with a class 2 combustible liquid that has a vapor pressure. Then you can determine it and say, okay, it's a volatile flammable liquid. And so where the code says you deal with those, then you at least you know what it is. So when it makes obviously the definition is here because it makes reference to volatile flammable liquids up in other articles of the code, most notably probably Article 501, okay? Because that's dealing with flammable gases and liquids. You with me? So because it makes that reference, here we go. But it could, obviously it's here, so it could be in other articles as well that you have to deal with, all right? All right, so with that said, we have finished all that we're going to cover in definitions. I encourage you to remember that as we move through the code, we're going to come back and look at certain definitions. That's why we skipped some of them because I know that they're heavily covered later on in our program. So I just wanted to make sure that we cover what we covered now so you get that foundation. And now we're going to move into Article 110. Okay? So stay tuned, and I'll see you next time on the next episode.
Shut up and sit down.